Welcome to our second lecture on astronomy. Last lecture, I started on the solar system and I got through the planets. And I was supposed to get to stars today, but I want to make sure that we understand a little more about the moon and eclipses and that kind of thing before we get to it. So let's review real short. What are the things in the solar system? Well, the obvious thing is the sun, which is a star. It's the dominant object in the solar system. Then the next most dominant things are the planets, and you need to know the order. So starting with the sun, the closest one to the sun. So if we put the sun up here, then we have Mercury, Venus, Earth, Mars. That's the end of the terrestrial or inner planets or rocky planets. Then Jupiter, Saturn, Uranus, and Neptune. And so we learned about these, and let me just highlight some of the key distinctions. So Mercury and Venus have no moons, none at all. Earth has one moon. Mars has two moons. Those moons, I didn't name them or talk about them, but those moons are Phobos and Deimos, or fear and terror. They're both captured asteroids, it appears. They're not big moons like our moon. Jupiter has 4 major moons. That is, large moons like our moon, although as we saw, the closest one, Io, is very volcanic because of the tidal flexing. The others are icy exteriors with then liquid underneath and rock underneath that. Plus, it has lots of small moons or minor moons. And we believe it got those moons by just capturing asteroids. Saturn has 1 major moon, plus lots of small moons. Uranus has, I can't think of any major moons for Uranus, but it has lots of minors. And then Neptune has a major moon. Triton. Saturn has Titan, Neptune has Triton. So everything that is beyond Venus has moons. What about atmospheres? Well, it's silly to talk about atmospheres for these because they're gas giants. They all have atmospheres because that's what they are. The Earth and Venus have significant atmospheres. Venus' atmosphere is approximately 100 times thicker than the Earth's. Mars has a very thin atmosphere, approximately 1/100th as thick as the Earth's. And so we have here examples of greenhouse effect. Venus has a runaway greenhouse effect. Its atmosphere is too thick, has too much greenhouse effect. And as a result, it's a very hot temperature planet-wide. The Earth has a greenhouse effect, that's just right. And Mars has too small of a greenhouse effect so that its temperature varies quite a bit. And during the daytime, it's nice and comfortable. And during the nighttime, we would be popsicles. So just some comparisons for the planets. So now let's move on. What's the shape of the Earth? These days, you can't go to social media without finding people who believe sincerely that the Earth is not a globe, that the whole globe Earth is some kind of conspiracy promulgated by some random people for some random reason. All the randomness of these things leaves me confused. So let's just review things we know. The shape of the Earth. Aristotle concluded from observations of the curved shadow of the Earth on the moon during an eclipse. So when you have a lunar eclipse, you see a curved shadow go across the moon. And he said that must mean that the Earth is a circle. Now it doesn't have to be a sphere, it has to be circular in shape, right? with the sun on one side and the moon on the other. But of course, how do you have a circle with the sun on one side and the moon on the other when we see the sun in the sky? You put that together and it really has to be a sphere. He also noticed that there are some stars that if you move farther south, you can see them in the sky. But if you move north, you can't see them. In this picture, what you have is a person standing up here near the North Pole, and it shows their horizon as this dashed blue line. If the Earth is a sphere, there's going to be a horizon, and they can't see anything below that horizon. If the Earth was flat, that is, the Earth would be like this, and it wouldn't matter where you are on the Earth, you would always be able to see the same stars. So those are two lines of reasoning that Aristotle came up with to say that the Earth was a sphere. Now, soon after, let's do this first. If Aristotle determined that the Earth was spherical in 350 BC, that's 350 years before the birth of Christ, who thought the Earth was flat in 1492 AD? That's 1,492 years, Anno Domini, or in the year of our Lord, after the year that Christ was born. Now, I should point out those years aren't exact, but that's not an issue here. There is often told that Christopher Columbus convinced Queen Isabella that the Earth was spherical and thus he could have a faster trade route to India by going the other direction. That's just not true. Who thought the Earth was flat in 1492? Basically no one. Everyone knew the Earth was flat, but Christopher Columbus didn't believe Eratosthenes. He thought the Earth was smaller. So that there would be a quicker route going the other direction. And Washington Irving is the person, from what I have read, who is credited with promulgating the myth that people thought the Earth was flat. Okay, so back to the shape of the Earth. Aristarchus, you notice he lived a little bit after Aristotle. He used the relative sizes of the moon and the Earth's shadow. That is, when you have an eclipse, you have the Earth's shadow out here, and the moon enters it, spends some time in it, and then exits it. And so by measuring the time for the moon to go through, he determined, well, not just the time, the curvature of the whole 9 yards. He determined from the shape that the moon was about 1/3 as large as the Earth. And he's not that far off. It's actually closer to a quarter, but he was in the ballpark. He also estimated the distance to the moon by timing. So, timing how long it took to go that distance. And he came with the moon was about 70 Earth radii away, which is not bad. So these are rough numbers, and they're based on the radius of the Earth. And of course, the radius of the Earth will affect what the measurement he has for the size of the moon and the distance of the moon. He then tried to determine things about the sun. So this here is what we call a quadrature when you have that right angle. But when the moon is half lit, he said, okay, that must be pretty simple geometry. We are looking edge on, so it's a right angle right there. Right angle, the sun is shining on one side of the moon, and half of what we see, the sun is shining on, half we don't. And so using that and the distance he had for the adjacent side, he then calculated what the distance from the Earth to the sun was. And he estimated the distance to be 20 times the Earth-Moon distance. That's not close. And then using that, he he said that the sun is about 7 times bigger than the earth. Once again, that's not close. So he didn't do so good on the sun measurements, but it was good reasoning along the way. Now, if we go back historically, people thought that the earth was stationary and that everything went around the earth. And a primary reason for that was that they didn't feel the earth moving. Now, if you talk to flat earthers, they still appeal to that same thing. I don't feel the earth moving. According to the ball earth, as they call it, the earth is spinning on its axis. And so if you're at the equator, you're traveling over 1,000 miles an hour. I forget what the actual number is, but you're going very fast. And so you should feel a very stiff breeze. You should be blown off your feet. It sounds reasonable until you stop to think, but wait, this air has some friction. And just like the water has a friction that makes it so it travels with the earth, the air has a friction that makes it travel with the earth. And if you've ever gone to a science museum, you will see places where they show you weather patterns, and you have a globe that spins with water around it, and you see, oh, look, the water is traveling with it. Well, that's what happens with the air too. The air is traveling with us. The air is going around the earth the same speed the surface of the earth is moving, so you don't feel it moving. But you do see the stars change due to that rotation as their positions change. Now, another point that people used to say that the earth was stationary was that they didn't see parallax. And parallax is a little harder to explain. If you ever looked at a dial on, some kind of device, the dial has a needle, and then behind that needle you have numbers. So a traditional speedometer might have that, or your fuel gauge in your car. And you may have noticed that if you're in the passenger seat and you look at the speedometer, you're going to see the needle on a lower speed than the person that's right in front of it, because you're looking at an angle. Well, that's what parallax is. It's an apparent change in position based on where you're viewing from. And so ancient scientists did not observe any parallax. That is, they didn't observe stars moving with respect to other stars. And so they concluded that we must be stationary, not changing our perspective. Well, as we have developed better optics and telescopes so we can look at things and see them magnified, we actually have been able to observe parallax. It really is something that occurs. It's just we couldn't observe that with the naked eye back in the day. So there's some arguments that have been made about, the earth being the center of the universe and everything going around it. So Aristotle believed that the earth was the center of the universe and everything went around the earth. And there were people who suggested that he was wrong at the time of his life, and they continued on. But his model was actually the prevalent model for about 2,000 years before the work of Copernicus and Galileo and Newton kind of knocked it off, and people realized it couldn't be right. But let's stay with the ancients. Eratosthenes, he lived he died about 200 years before Christ was born. By the way, BCE is before Common Era. Common Era is the same as AD. AD, Anno Domini, the year of our Lord. Common Era takes out a reference to the Lord. BCE, before Common Era. So BCE is equal to BC, before Christ. The whole point of that is to try to not use the name of Christ in the years. It's, some people are just offended by that. So Eratosthenes, he wanted to know the size of the earth, and he noted that the sun could be seen at the bottom of a well in Syene on a certain day. And if the sun could be seen at the bottom of the well, that meant that the sun had to be directly overhead. And so he got this idea. And so he has somebody at the same time that he's measuring this, in Alexandria, measure the angle of the shadow of the obelisk in Alexandria. And that angle was measured to be about 7 degrees. And so Eratosthenes said, aha, then there's about 7 degrees angle from the center of the earth between Syene and Alexandria. And then using the rule that the arc length S is equal to the angle multiplied by the radius, then the radius of the earth must be that arc length divided by the angle. And of course, you have to use the right units. You have to use radians here. And so measuring the distance between Syene and Alexandria and dividing by this angle in units of radians, he calculated the diameter of the earth to be 13,000 kilometers, which is almost exactly correct. So here, over 200 years before the birth of Christ, not only did people know that the earth, the educated people know, that the earth was a ball, but they knew the radius of the ball almost exactly. Nowadays, we can measure the size of the sun fairly easily. One way we can do it, and this is what we would be doing in lab this week, where we back at school, is we can use a little pinhole and we measure the distance from the pinhole to the ground, or wherever we're having our image, and we measure the diameter of that. And then we say, okay, the distance from the sun to our pinhole, which is essentially the same as the distance from the sun to the earth, because the distance from our pinhole to wherever we're viewing is going to be very small compared to the distance from the sun to the earth. That and the diameter of the sun are going to have the same ratios. So you put diameter of sun divided by the distance to sun is equal to the diameter of the image divided by the distance from pinhole to image. Now, this has two unknowns for the sun, the diameter of the sun and the distance to the sun. So you have to know the distance to the sun if you're going to calculate the diameter of the sun. But that's how we actually could measure the diameter of the sun if we know the distance. That's what we would have been doing in lab. Something that you certainly have observed is that the moon goes through phases. And why the moon goes through phases is actually really, really simple. The moon goes through phases because the Earth is a sphere and the moon orbits around the Earth and the Earth orbits around the sun. So we're going to put the sun at a fixed position for our argument's sake here. So the sun is back here. And if the moon is between the Earth and the sun, then the sun is going to light up to half the moon we don't see. And we see what we call a new moon because we see no light reflecting off the surface of the moon. Something that's important to know is that the moon does not give off its own light. The moon reflects light. Stars give off light. Planets and moons and that kind of thing reflect light. So if you don't have light hitting the surface of the moon facing you, then there's no light to be reflected. Well, as the moon moves around the Earth, here, if you look at the moon from the Earth, you're going to see most of the moon is still in shadow, but a little edge is lit up. And so you have just a crescent there. We call it a waxing crescent. Waxing because it's growing, crescent, well, because it's the shape of a crescent. If you keep going, you get here to what's called the first quarter, and this is that angle that we looked at before, 90-degree angle between the sun, the moon, and the Earth. In that case, one half of the moon is lit up, one half is not. So it's a half moon, also called a first quarter. Keep going, it's still waxing because it's growing. Over here, now if you look at the moon, what you see is most of it is lit up and only a small fraction is not. So that's like this here, and we call that a waxing gibbous. Gibbous means humpback or pregnant. And then finally here you have a full moon because the sun is lighting up the entire side of the moon that the earth sees. And then it's going to wane, that is, the amount that we see lit up is going to decrease, so we have a waning gibbous. Third quarter, it says last quarter here. You might wonder, why is a half moon a quarter? Because it's a quarter of the way through the cycle for first quarter. A full moon would be second quarter. Third quarter is another half moon, and then we're still waning. We get to the crescent and the new moon. The time it takes to do this is what we call a month. There's actually two cycles, one measured from full moon to full moon, and that's the synodic period. And then there's the sidereal period, the time for it to do one full orb around the earth. The two are not the same because the earth is also going around the sun. And because the earth is going around the sun, the synodic period, the time from full moon to full moon or new moon to new moon, is about a day and a half longer than the sidereal period. So sidereal is relative to the stars. The side there means star. So sidereal is relative to the stars. The sidereal period for the moon is around 27 and a half days. Was it 27.3 days? And then we have the synodic. That's for the light cycles of the moon, and that's around 29 days. So for most purposes, we're simply going to stick with the synodic period. And so the month, now how long is a month? Well, 30 days has September, April, June, and November. All the rest have 31 except for February. It's a little bit different from 29 days, but it averages just a little over 30 days in a month. And you might wonder, well, the month is named after the moon, right? So shouldn't it be the synodic period? Shouldn't it be 29 days in a month? And the answer is I'd say reluctant. Yes, it should be. But we have a different reason for the months. We want the months to break up the year. And 1 year has 365.2422 days in it. I put the A and the Y in opposite positions. And so the months are designed to break up the year into 365 days. And then every 4 years, we add a day. And then every 100 years, we take out a day. And every 400 years, we add a day back. That whole leap year system gives us the 365.2425 days in the year. That's what our calendar actually is based on. That's why we have leap days, leap years. So the moon, or the months, are divided up so we have an even number of months in a year, and that's why it's not 29 days in a month. So what causes us to have the cycles of the moon? It is the moon's orbit around the earth. Now, you might wonder about eclipses, and we'll see eclipses just a little bit. During the time of a new moon, where is the sun, the earth, and the moon? So here's the earth. Here's the, well, that's not the right position anyway. Here's the sun. A new moon is when we have no light, that's sunlight, reflected off the portion of the moon we see. So if the sunlight is shining like this, then the moon, I'm just going to put a random position for the moon. If the moon was up here, this side is lit and this side is dark. And from that angle, we would see just a little bit lit. But if we move that down, if we move it down so it's directly between the sun and the earth, then we only see the part that's unlit. And so for a new moon, the moon must be directly between the earth and the sun. Now that brings up the idea of the eclipse. What is an eclipse? An eclipse is when the shadow of either the moon falls on the earth or the earth falls on the moon. So here is the geometry that you would have for a new moon. And if they truly form a straight line, then the shadow of the moon is going to fall on the surface of the earth. It's a small shadow. And in fact, the Earth-Moon distance varies just a little bit, and the Earth-Sun distance varies just a little bit. So sometimes the shadow ends before you get to the surface of the Earth, in which case we have what we call an annular eclipse. If you look at the sun during the annular eclipse, you see an annulus. You see the moon blocking out the center part of the sun, but you see the sun around it. And sometimes you have a total eclipse, which covers a region of the earth, such as what we had a few years back here at Union College. And that's going to occur when the moon is a little closer to the earth or the sun is a little farther away from the earth. So why don't we have a solar eclipse every month, right? If that's the geometry, if the new moon geometry is the geometry for solar eclipse, then it seems we should have one every month. The reason we don't is for a simple reason. We have the sun, and we have the earth that's orbiting around the sun in a plane like this. The plane that the earth is orbiting around the sun we call the ecliptic plane. Well, the moon orbits around the earth, but the moon orbits on a plane that's tilted approximately 5 degrees from the ecliptic. So most of the time, the moon is going to be either above or below the ecliptic when you have a new moon. And in that case, the shadow of the moon is going to fall outside of the earth, right? The moon, well, you can't draw it on a two-dimensional picture, but the moon is above or below the plane of the screen, and so its shadow doesn't hit the earth most of the time. So it's because of this tilt between the moon's orbit about Earth and Earth's orbit about the sun. That's why we don't have a solar eclipse every time we have a new moon. Instead, we have a solar eclipse about once a year as the moon goes up and down on its orbit about the Earth, and the Earth goes around the sun. So when the moon is crossing the ecliptic, we call it eclipse season, because if you have a new moon, then you'll have a solar eclipse. Or the geometry for a lunar eclipse is when this here now is the Earth and this is the moon. So when the moon falls within the Earth's shadow, we have a lunar eclipse. When the moon is not reflecting light, when it should. Notice this is the geometry when we should have a full moon. But once again, if the moon is in the same plane as the ecliptic, then the Earth's shadow falls on it and we have a lunar eclipse. Now, notice how much of the moon is in the shadow, the entire thing, right? And what parts of the Earth are going to see the lunar eclipse? Any part of the Earth that is able to see the moon, which means 1/2 of Earth sees the lunar eclipse. So if half the Earth sees a lunar eclipse and you have, on average, one lunar eclipse a year, then you're going to see, on average, a lunar eclipse every 2 years. It's not a rarity. But if you're doing the solar eclipse, then it's just a tiny fraction of the Earth that has the full eclipse. Which is why the solar eclipses are considered so much more cool, because it's so rare to see those. You have to be just the right spot. So Lincoln was in the path of totality. Notice as the Earth and moon move, where the shadow of the moon strikes the Earth is also going to move. And so there's a path that went from Oregon down to roughly, I think it ended in Tennessee, might have been all the way to Florida. So they called it the Great American Solar Eclipse because it went across the entire country, but only in a narrow path. And so people flocked to those regions. And of course, we had a cloudy day because, that's life. But if you were at Union College for the eclipse, you should have noted that the sky got darker. And we were able to look at during the totality of the eclipse, we didn't have to wear our glasses, and we could look at the sun, because the moon was completely blocking out the sun, and all we would see would be the corona around the sun. So those are eclipses. Here's a picture of the moon just coming out of an eclipse. So you have some light hitting down below this line here. It looks red in the part that's eclipsed, and that's actually because of refraction, because of light bending around the Earth through the Earth's atmosphere, hitting the moon. So there's no direct sunlight hitting it, but there's light that bends around the Earth that hits it, giving it that red color. Now, asteroids is something I didn't talk about in class yesterday. Well, not yesterday, 2 days ago. In truth, I did the lecture yesterday. Asteroids are basically rocks. They're small bodies that orbit the sun, and there is a large asteroid belt that falls between Mars and Jupiter. So if you look at remember we had Mercury, Venus, Earth, Mars. Those are the terrestrial planets. Then we had Jupiter, Saturn, Uranus, Neptune. And in between the orbits of Mars and Jupiter, we have an asteroid belt, a belt of asteroids. Now, by watching science fiction, you get completely wrong perceptions about asteroid belts. The asteroid belt is a belt that has less mass than a planet. The entire belt is less mass than a planet, and it's mostly empty space. So if you're trying to navigate through the asteroid belt, it's not some scary, hard process. It's mostly empty space, so you just go straight through for the most part. If you're unlucky, you have to swerve once. But these asteroids are rocky items. And we look for asteroids on the ground. If you're looking at ice, you can find them because they will stand out compared to the ground, because sometimes asteroids fall into the Earth's orbits. Asteroids are not just between Mars and Jupiter. There's also what we call Trojan asteroids that are traveling with Jupiter, and there are asteroids spread out very sparsely throughout the solar system. Now, comets are a completely different thing. Comets are dirty ice balls. They have some rock, but they have a lot of ice. And that ice isn't just water ice. It's water, methane, different volatiles. Ammonia is another one, that are all frozen. And these are located either in the Kuiper Belt or the Oort cloud, places that are beyond the planets. I say beyond the planets. Pluto is in the Kuiper Belt. So Pluto is an example of what we call a Kuiper Belt object. And our comets are objects like Pluto. But what's the difference in a normal Kuiper Belt object like Pluto and a comet? Comets have highly elliptical, that's very eccentric orbits. So here's the sun, and the path of a comet, okay, I should have done the path of the comet and then done the sun. The sun is like here. And so that comet is going to sometimes be close to the sun, sometimes far from the sun, and actually, to be accurate, I should put it even closer there. It should be, yeah. So most of the time, the comet is very far from the sun. When it's far from the sun, it goes slow. So it moves very slowly out here, so it spends a lot of time. But then when it falls in, it goes very fast as it gets close to the sun. So we have, Pluto. Pluto's orbiting around out here. Pluto has a fairly eccentric orbit, but not compared to this. Pluto's orbit, sometimes Pluto does come closer than Neptune. It crosses over Neptune's orbit, so sometimes it's closer. Most of the time it's farther. But it's still very circular compared to the path of a comet. So when the comet's out here, it's an ice ball. Plain and simple. But when it comes close to the sun, then the sun starts evaporating material and blowing it away. And so it will have a tail that's blowing away from the sun of material that was vaporized by the sun. The sun has what we call the solar wind. It has charged particles like protons and whatnot flying away from it. And so those hit the tail of the comet and push it away from the sun. You also have electromagnetic waves traveling away from the sun, and those further push the tail away from the sun. So as the comet comes around the sun, its tail is always pointing away from the sun. We often think of the tail as trailing behind. Not so. It's pointing away from the sun. And so when a comet comes around the sun, it loses a lot of material, which means the comets only have a certain number of laps they can do before they're going to be destroyed. So once again, we as creationists, sometimes people say, look, we have comets. Comets can't survive more than X number of trips around the sun. X would depend on the size of the comet and how close it gets to the sun. So the fact that we still have comets means that the solar system must be fairly young, 100,000 years or less. Well, here's the flaw to that. What makes a comet go from like Pluto's orbit? Almost all of those Kuiper Belt or Oort cloud objects are doing circular orbits roughly around the sun. What makes them all of a sudden come in on these highly eccentric orbits? And the answer is a close call with another object. So like if Pluto passes close to another object, the gravitational pull of Pluto will perturb the orbit of the other object, making it change directions, and that's really what causes new comets to happen. So new comets do happen. In fact, about 4 years ago, there was a Christmas comet, and it was supposed to be spectacular. It was going to be a Christmas comet. It would be almost like when Christ was born. Some people say that what the angels saw must have been a comet. Well, unfortunately, that new comet, it did happen. It came in, but it got too close to the sun, and much like Icarus, it got destroyed. And so we didn't have our amazing Christmas comet because it didn't survive one lap around the sun. Once its orbit got perturbed to make it fall toward the sun, it came too close to the sun and was destroyed without making it around the sun once. So it was a one and done comet. new comets can occur is the point. So the fact that we have comets does not mean that the solar system has to be, less than 100,000 years old. So here's a picture illustrating what I've just been talking about. The normal orbit of the Earth is shown down here in blue. In roughly white, we have the orbit of the comet. And you see that the comet is just a frozen ice ball when it's far away from the sun. When it gets closer, it starts to boil off, or sublime. Actually, sublime means go directly from solid to gas. And as it gets even closer, the sun blows that material away from the sun. And notice it shows two tails. This one, the ion tail, points directly away from the sun. The dust tail is not charged, and it's mostly away from the sun. Here's a picture of the night sky. What you see here is the result of millions of stars. Millions of them. And so those stars, you see this thing right here? Okay, I changed to red because red will stand out better. This thing right here, it's a dark region. That's the Milky Way. The Milky Way is a big collection of stars and dust. And we're part of the Milky Way. Our sun is part of the Milky Way. And so you see all of the light back here, that's light from stars in the Milky Way. All of this here is actually stars in the Milky Way as well. So what's making this dark? That's gas that's in the disk of the Milky Way. We ourselves are in the disk of the Milky Way. The Milky Way is kind of shaped like a frisbee. And so the center part is the disk, and we're in there. And as we look around in the disk, there is dust and gas all along that distance, or direct all along that plane, and it blocks light from stars further away. So we see a lot of gas and dust there, making it darker. If you go above or below, you don't have as much gas and dust, and you see more of the stars. So when you look in the sky, virtually everything you see in the sky is part of the Milky Way. When you look at the disk, you see what looks like a cloud. That's actually how they got it the name. They said it looked like a trail of milk, Via Galactica. And so translated to English, that's the Milky Way. This out here, those two things are not single stars, those are galaxies. So those are other, by the way, the Greek for Latin is Via Galactica, which is where we get galaxy from. And the Greek is, or Via Lactea, is the Latin, Via Lactea. And the Greek is Galaxia Kuplos, I think it is. And so galaxies comes from the Greek. But those are two galaxies out there in the picture. So there are a few galaxies that you can see even with the naked eye. With the naked eye in the northern hemisphere, you can see the Andromeda galaxy. That's the only naked eye galaxy in the northern hemisphere. In the southern hemisphere, there are two more called the Galilean clouds because, or Galilean, not Galilean. They are the, what is his name? Magellanic clouds. Because Magellan, when he was circumnavigating the globe, his sailors saw those two clouds in the sky, and it turned out we now understand that they are galaxies. They are other collections of stars all orbiting together. So when we look in the sky, everything you see, with the exception of one thing in the northern hemisphere, and that's the Andromeda galaxy, is a star. Now, if you use a telescope, you can see more details and you see more things besides the stars. And all of those stars you see are within our galaxy. When you're observing the sky, there's a few terms that are good to know. One is zenith. The zenith is straight over your head. There's a word for the opposite of straight over your head, nadir, directly under your feet. But of course, you can't see your nadir. And the horizon is going out, as luck would have it, horizontally. So when we look up, if you look straight up over your head, you're looking at your zenith. Now, the Earth, because the Earth is spinning, we see a north celestial pole, which is the place where the stars appear to rotate around a point. So you've seen pictures that show motion of stars at night. And here you can identify then, this is the pole. And all the stars are doing circles around that, it looks like. What's really happening is the Earth is rotating. As the Earth rotates, those positions of the stars relative to the Earth move because of the Earth's rotation. And so these pictures are very clear indicators that either the Earth is rotating about a pole, what I believe to be true, or that the entire sky is rotating, which is a much more complicated thing to imagine. So those pictures are showing you how the Earth is rotating. And so if you were at the North Pole, you would see those rotating about your zenith, about a point directly overhead. But if you're here in the Northern Hemisphere, like we are, we're about 40 degrees north of the equator, then you're going to see this here would be about 50 degrees if this is 40 degrees. And so about 50 degrees from your zenith or 40 degrees from your horizon is where you're going to see that point where the stars all appear to be rotating around. The celestial sphere is a model. It's a supermodel. It's not real. It's not something that is actually there, but we treat as if all of the stars are located on this sphere. It's easy then because we can talk about the relative positions of the stars based on the rotation of the Earth within that sphere. Or as we tend to think of it, the rotation of that sphere around us, because we feel ourselves as stationary, and so thus we make the approximation then that the whole universe must be rotating around us, when in fact it is simply us that's rotating. Now, just a few more terms, and I'm going to end the lecture. So the zenith is straight over your head. So here's a person. Is there a person? Yeah, there's a person right here. And so that person's zenith is going to be up here. Their nadir is directly underfoot, so there's their nadir. The horizon is off to the side, so that's the horizon. And then we have the celestial equator. We have the Earth's equator, which we understand is halfway between the poles. And if we just extend that out to the celestial sphere, it will put a circle on the celestial sphere, and that's the celestial equator. Now, the Earth orbits the sun, and because the Earth orbits the sun is at a fixed, compared to this orbit, the sun will be at a fixed position. As the Earth goes around, the sun's, where it's striking the Earth, moves north and south. And so we have the tropics is the region where at some point during the day or during the year, the sun will be directly overhead. The tilt between the Earth's axis of rotation and the axis that the Earth orbits around the sun is about 23.5 degrees. And so that means sometimes we're going to see the sun is 23.5 degrees below the celestial equator, and sometimes 23.5 degrees above the celestial equator. And so that's the tropics is plus and minus 23.5 degrees from the celestial equator. And the Arctic and Antarctic are likewise the Arctic Circle, there's an Antarctic Circle, 23.5 degrees from the poles, because The Arctic Circle or the Antarctic Circle describes the position where you're going to have at least one full day when the sun neither rises nor sets. Now, I have a picture coming up, just a couple more slides, that shows the geometry better. So here we can see that tilt of 23.5 degrees. And we have in June, the sun will appear on the as far north as it ever does, and we call this the summer solstice. So the summer solstice is when the sun is 23.5 degrees north of the celestial equator, and it occurs roughly June 22. We have the winter solstice, which is when the sun appears 23.5 degrees south of the celestial equator. And in the northern hemisphere, that describes the start of winter. The summer solstice in the northern hemisphere describes the start of summer. And then there's two locations that we call equinoxes. When the sun is directly above the celestial equator. And so we have the spring or vernal and the autumnal equinoxes, and those are what start the season. So spring starts around March 21 when we have the sun crossing the celestial equator. And we have the autumnal equinox, the start of autumn, approximately September 22, when once again the sun crosses the equator, the celestial equator. So our seasons are defined by this tilt. And when the sun is in the northern part of, north of the equator, we get more direct sunlight. That means we get more heating, and thus the temperature rises because, as we learned, the heat is equal to MC delta T. So if the heat is greater, then the temperature is going to rise. If the heat drops, then, well, it's going to drop. Okay, now final thing, signs of the zodiac. The zodiac basically means the zoo. And the signs of the zodiac are the constellations that the sun passes through as viewed from Earth. Now remember, in fact, the Earth is moving around the sun. But as viewed from Earth, we see the sun moving through the constellations. And so on the day I was born, the sun was right about here. And so that is, the Earth was here, and so we saw the sun about there. So you would think that I would be a Libra, right? Au contraire. Au contraire, because when we changed the calendar system back in the 1600s, because they didn't have the leap year system, so that they skipped they just had a leap year every 4 years up until the 1600s. And because of that, the seasons were slowly moving. And so they adjusted the calendar by, depending on where on Earth you were, 10 to 11 days. And so it turns out they didn't change the signs of the zodiac on the calendar. And so I am a Scorpius, even though the sun was in the middle of Libra the day I was born. It's supposed to be your sign of the zodiac is where the sun is viewed from Earth on the day you were born, but it's off. And since there is no science behind astrology, it is what we call pseudoscience. They use scientific information, the position of the constellations of the sun and the Earth. They call it a science, but it's not a science because they draw conclusions that aren't based on scientific ideas. And with that, we'll end the lecture. Have a swell day.